Hey guys, good to be back. In this tutorial now I want to talk to you about random networks a little bit. We already talked about random networks before. What is a random network? How would we define a random network? There's a Bernoull graph or a Renyi graph, which is a graph where each tie has the same random probability to exist, yes or no. Right? That's sort of like one way we can go about it. There are other ways of generating random networks. But one thing that is important for us now, especially when we start talking about hypothesis testing on networks, is that networks, even when you create them at random, they exhibit non-random attributes. That's kind of odd to wrap your head around. So why is that? Well, think about a network where everybody is connected with everybody else. Yeah? How many triangles do you observe? Well, the maximum number of triangles that you could observe in that network. You could actually go and manually calculate that. While in contrast, let's say you have a network with 10 nodes and 2 ties in it. Yeah? So 2 lines in it. How many triangles do you observe? Well, you can't observe any triangle because there are only 2 ties to begin with. Right? So you see the number of ties or density. Density is just another word for how many ties exist out of the ones that could exist. With increasing density, you will observe more triangles in a network. That's just one of those basic things, where network properties really depend on how many ties there are. So now in this tutorial, I want to simulate random networks with you. So how do we go and simulate random networks? Well, there's one command that we start using here, and that's rgnm. Let's look it up. rgnm. rgnm, there we go. That's the help file. It's in the SNA package. It says draw density conditioned random graphs. Okay. rgnm generates random draws from a density conditioned uniform random graph distribution. Density condition means it creates a network that has a certain density. Yeah? So a certain amount of ties. When you look up the usage again, so how does it look like? rgnm and then n and then nv and then m and then mode. So these are the different arguments. What are these arguments? N is the number of graphs that you want to generate. Okay, so maybe just set this to 1. NV means number of vertices, the size of the vertex set. So how many nodes should your network have? And M being the number of edges on which to condition. So basically the number of edges that you want this network to have. And it calls it to condition because it only picks random networks that have that many ties in it. And then lastly, and then I'm going to run the command, it says mode. There we can specify the digraph or graph, digraph on directed graph or graph on undirected graph. So whether it has an arrowhead attached to it or not, the type. So let's run that in a very simple way. So I have like one line, rgnm 1, 100, 200, and mode digraph. So remember the first number, n, was the number of graphs. To be precise, I should do something like this. N equals 1, then nv equals 100, and then m equals 200, and mode equals digraph. Yeah. The other way would have worked as well because it kind of remembers the order of it and then it just assigns it automatically. But this is sort of like the cleaner way for you to see what happens. When we run this command and I assign whatever comes out of that into something that I call graph1. Okay, that worked. So what is graph1? It's a matrix. Great, we have a matrix. Let's look up a matrix, graph1. And I regret looking that up because it's a matrix that has 100 rows and 100 columns in it. Yeah. Let's do something else. Remember the last tutorial we used the table command on a matrix before. Let's do that. graph1. And now, what do you think we're going to find? Maybe you want to pause here for a second and think about what this command is going to show. Okay, well, it's very straightforward. There we go. Great, it worked. It says for 9,800 entries in that adjacency matrix that was generated by that, there's a value of 0. And in 200, there's a value of 1. Why 200? Well, because that's what we exactly set up here. So we said create a network with 100 nodes, NV equals 100, and 200 edges in there. There are the 200 edges. So we have an adjacency matrix with 200 ones in there. And they're randomly assigned, so we don't really know where they are. And every time you would rerun that, you would get a different assignment of those ones onto that adjacency matrix. Okay, now we have an adjacency matrix, and the next step is pretty straightforward. It's stuff we've already done. How do we create a network object? Well, we just use the network command and we give it as an argument a matrix, an adjacency matrix. And now we don't even have to specify anything else about directed, because by default it sets directed to true anyway. Okay. So we can take that out. We want to create a direct network here. Now we have something called r-net. What is r-net? Look it up. It's a network object, and here you see it. There's 100 nodes in it. There's 200 edges in it. And that's our first random network. Great. Let's plot that. r-net1. There we go. And that's a random network with 100 nodes and 200 edges in it. That's pretty straightforward. So now each tie had the same chance to exist. Right? And at the end, the algorithm works in such a way that it always comes up with networks that have m number of edges. In this case, we specified it with 200. Right? If we would change this number here, it would generate a stack of 10 different graphs, right, instead of just one. That's for another thing. Okay, so that's the first network that we generated. Well, I've already done that. So we don't really need that. Let's look at another command, how we can generate a random network. There's a command called rgraph. So what does that do? Generate Bernoull random graphs. Again, it's in the SNA package. rgraph generates random draws from a Bernoull graph distribution with various parameters for controlling the nature of the data so generated. What is a Bernoull graph? A Bernoull graph is one, again, where nodes either have values 0 or 1, and where each tie has the same probability. Now this command works slightly different. That's sort of just great about R is like, I don't know, sometimes the arguments are called in a different way. Now we have something that is called n, and that is not nv anymore, now it's called n, and now n is the size of the vertex sets. So now, I don't know, so n equals 100 doesn't generate 100 networks, but it generates one network with 100 nodes in it. And then the next number, m is the number of graphs it generates. M equals 1, so it just generates one graph. So that's a slightly different notation from the rgnm command than we had before. Now the decisive thing is tprob. What is tprob? Information regarding tie edge probability. So that's really just the probability for a tie to exist. Yes or no? When I set this to 0.02, it's just really a 2% chance that a particular tie from node A to B exists. So that's all. So let's run that. It generates, I save it in something called r-graph. Again, it generates a matrix. There we go. Now we could actually look up and look at how many nodes are in there, how many ties are in there. And now you see, that's kind of like a little, now we have 193 ones in there. Why do we not have 200 in there? Let me run the same thing again. And now you see something else. Oh, now we have 211 ones in there. Why do we not have 200 in there? Think about that for a second, pause, and then maybe you come up with a solution. Okay, the answer is straightforward. The answer is really because it's a probability for each tie to exist, right? Every time it's like flipping a coin, sort of, with a probability of 2% that it's a 1. So sometimes you do get a 1, sometimes you don't. But it's not conditioned on something. It's not conditioned on a certain amount of ties that will be there. So if you do this many times, on average, you will have around 200 edges in there. But sometimes it's a little more, sometimes it's a little less, because each tie from A to B has a probability to be there, yes or no. So that kind of brings in a stochastic component. Sometimes you then have more than 200, sometimes you have less than 200 in this case. Okay, so we again have like a graph, and now the next thing is exactly the same thing before. We take that matrix, that graph is saved as a matrix format, r-graph2, that's a matrix, and we take that as an input, generate a network object, save that, call it r-net2. There we go. Now we have like a network with 100 nodes and 211 edges. Got that. There we go. That's another random network. But now not with exactly a specific number of edges, but with each tie having the same probability to exist. Okay, well, I talked a little bit about why that is the case. Let's now do something else. I actually want to show you what I just said earlier. Now I run that command, and instead of creating m equal 1 network, now I create 500 networks. See how easy that is? Actually pretty awesome. It's pretty easy. R graph 100 nodes, n equals 100. Yeah. 500 times, so create 500 networks, and each tie has the probability point to 0, 2% to exist there, yes or no. It takes a little bit of time, and now we have, I don't know, let's look up, what is it? It should still be, it's an array now, okay. It's an array, and if I would kind of floated that, and I'm going to regret that, because now I don't just get one matrix, but actually there are now 500 matrices, and you can confirm that by looking at the dimensions of that thing. Now you see it is a 3-dimensional array, where 500 means like each network, and 100 times 100 is now the adjacency matrix. Right? So Erdős graph, Erdős graphs, now 1 and now comma. What does that do? It takes the first network. Now I have a network of 100 times 100. It takes the second network, and so on. There we go. And so now I have this array, and now I can, well, we have this command gden. Let me just quickly run it up here. This is the density. The density, gden is the density. I calculate the density of a graph. Density of a graph, nothing else than how many ties exist in that graph divided by the number of ties that could exist in that graph. Yeah? So this here means like, I don't know, 2%, around 2% of the ties that could exist in that graph do exist in that graph. Now we have, when you have an array of networks, this gden command is actually pretty fancy because it allows you as an input not just one network, but lots of networks. So you can run gden now not just with one network, with Erdős graphs too, but with Erdős graphs, which is, remember, this is like this array. It's like this 500 times 100 times 100 networks. If I do that, now what I do, well, that's actually pretty awesome. Now I get 500 numbers, so for each one of those networks, I generated the density. Let's put that whole thing into the histogram commands, hist, and now you see what we get. Now we get a histogram, which shows us how many times it finds a network that has that much of a density. And what you see is that the average is around 0.02. Sometimes their density is a little higher, sometimes the density is a little lower. So this is now a way of how we very quickly generated 500 networks, and how you could see that this command, rgraph, with a certain number of tie probability, generates sometimes networks that have more ties and sometimes networks that have less ties. And that's because each relationship from A to B has a certain probability to be there, yes or no. And that's what's specified in the tprobe argument here. Okay, there's one other command that I want to do with random networks, something called rguman. Random graph uniform man, that's what this stands for. Man is the mutual asymmetric null Dyad. It's Dyad census, so it generates random draws from a Dyad census, conditioned on uniform random graph distribution. What does that do? Well, now you always need to read through the arguments here, because sometimes n means something else for the one command than for the other command. So here again, like n means the number of graphs to generate. Okay, there we go. Let's set this up. N equals 1. NV is the size of the vertex set, so how many nodes there should be. NV equals 20. Now it has these 3 other things that we can specify. Mut stands for mutual dyads, asym stands for asymmetric dyads, and null stands for null dyads. Okay, what is a mutual dyad? A mutual dyad, think about nodes A and B, and their relationships, the way they are related with each other, that's what we call the dyad. These 2 nodes, they constitute the dyad. And their relationship now, it could be that none has a tie to the other. In the world of a directed network, none has a tie to the other. That's actually a null diad. Could be that both nodes A and B send a tie to the other. Right? So like an arrow going into both directions. That's what we could call a mutual diad. Or it could be that only one of them sends a tie to the other, either A to B or B to A, but not the other way around. Right? So that's just one line going from one node to the other and one arrow attached to it. That would be an asymmetric diad. So now the RGU man command generates a network that has a certain amount of mutual dyads and a certain amount of asymmetric dyads. It's actually pretty cool because we can specify, then you see how we kind of now generate random networks that have a little more features to it, right? So I could generate a random network that only has mutual dyads, so only reciprocal relationships where one sends a tie to the other one also sends a tie back in a way. Or you could generate a network where you have none of those and you have only arrows going in one. These are all random networks, right? But they are sort of conditioned on something. And here they are conditioned on the diad census. Before we conditioned it on the number of edges, like how many edges should there be. Now we can condition it on the diad census. And let's do, I don't know, there are a couple of other options. Null, to be honest, we probably wouldn't have to specify this one. Sometimes it's easy just to leave that out because then you don't have to think about that for a moment. Otherwise you would have to calculate it. You can, because you really know how many dyads you have. You have n nodes, you have n times n minus 1 divided by 2 number of dyads. That's the number of dyads that you have. Method, the generation method to use probability results in a multinomial die distribution except as a uniform draw condition on exact diad. Okay, so let's use exact. So that means it generates a network that has exactly that diad census. Okay, so this is a little, let's see what comes out of that. It wants to have the number of mutual null dyads, so we do need to specify it. Okay. And this is actually now so I calculated that before. How did I calculate that? Well, I have 20 nodes. Yeah. Okay, 20 nodes. So how big is the adjacency matrix? Well, it's 20 times 19. That's the adjacency matrix minus the diagonal. Okay, how many dyads do I have in there? But a dyad just doesn't really care about the relationship. It's really just with the direction of the relationship. It's really just about a pair of two nodes. So how many dyads do I have? Well, 20 times 19 divided by 2. So there are 190 dyads in every network with 20 nodes. Okay, now I specify 50 of those should be mutual. So 50 of those, there should be a tie from A to B and from B to A. So there should be 50 pairs of nodes where that should be the case. And I say 100 of those, 100 other ones should be where one node sends a tie to the other one, but not the other way around. So 100 plus 50 is 150. So how many are left? Well, there are 40 left. So we have 90 minus 100 minus 50. There we go. And that gives us 40 dyads that need to be null dyads. That's where this number comes from. So you can calculate all these things in a straightforward way. Oops. Now let me run this command. There's another network generation command. What is random graph? Let's check random graph. Again, it kind of gives us probably a matrix. It's a matrix. Yeah. So this is a matrix. Now I could go and generate a random network out of it. Let's do that. Now I'm a little more, it would have worked without it as well, but let's be clear. Random graph, and it should be directed, so that's fine. So it generates a random network. Random net, there we go. It's 200 edges in there, and if you would probe into a why are there 200? Well, actually, there have to be 200. Yeah, when you think about it, so you have 50 dyads where there's a tie going in both directions. So how many ties do they have? Well, 50 times 2. Yeah? So that means you have 100 ties coming out of the mutual relationships and 100 coming out of asymmetric relationships, where just one sends but not the other one sends back. Together, that gives you 200 ties. That's where the 200 comes from over here. So we have this network, and now I'm using the command diad census. Let's use it on the network object. There we go. Diet census is a command. It would have also worked just with the matrix, but to be precise, use the network here. It tells us this network, RandomNet, has 50 mutual dyads, 100 asymmetric dyads, and 40 null dyads. And that's how you can generate networks that have a certain amount of reciprocity, for example. Let's say you want to generate a network where every a tie has a 50% chance to be reciprocated. If you nominate somebody, there's a 50% chance that that person also nominates you back. We generate a random network that has this feature now with conditioning on the Dyad census. Okay, so these are three different ways how you can generate networks. Let me just summarize. The first one used the RGNM command. RGNM generates a random graph with a certain number of nodes, in this case with 100 nodes, and with a certain number of edges, 200 edges, and I can specify is it a directed or an undirected graph. That was the first one. The second command was rgraph. What is rgraph? Rgraph generates a certain amount of networks. Now M stands for the number of networks. It's confusing, I know. But M now stands for the number of networks. N stands for how many nodes there should be. And Tprop specifies the probability that a tie exists between two nodes. So that generates networks. Sometimes they have a higher density, sometimes they have a lower density, but it should hover around 0.02 as the density. And I showed you that that actually is the case. And then the last one that I showed you is how you can generate a random network is a random network that is conditioned on a Dyad census. So you see how this is now, these are all random networks, but now think of it of the possible universe of all networks that could exist. The possible networks of all networks, when you condition on something, you say, okay, out of all of that possible network, draw only those networks that have certain features. And in this case, this command only draws networks that have a certain Dyad census. A Dyad census means like how many mutual dyads are there, where A sends a tie to B and B also sends a tie to A. How many asymmetric ties are there, where A sends a tie to B but not B to A. And how many null dyads are there, where A and B, nobody sends a tie to each other, to the other. So that's a null dyad. So that's how you can generate three different ways how you can generate random networks. And you also saw already how I used it in sometimes where you can generate more than one network, right? So just generating this number, for example, now I would generate 10 random networks that have this Dyad census, for example. Okay, so much about the second tutorial. In the next tutorial, I don't know what we're going to do, but we're going to figure it out. Okay.